Hey everyone, welcome to the first lecture of the calculus series by the ML Hub. So this will be an introductory session on functions. So in this lecture, we'll be discussing what exactly a function is, properties of function, which is domain and range associated with a function, types of function, which is composite function, and symmetry of functions. And the same time, we'll be solving few of the examples on these topics. Okay, so let's get started. Yeah, so when it comes to definition of a function, which is denoted by small f, is consist of a set of inputs, a set of outputs, and a rule. So this rule associates or bounds the set of input with an output, but with a very important property, which is assigning each input to exactly one output. So this term exactly is very important when it comes to what is a function. So if you see a scenario in which an input is associated with more than one output, in that case it is not a function. So it should be an exact mapping. Okay, one input should exactly map with one output. So if you see it, you can think of function as a black box. Okay, which binds two sets, set A and set B. Here set A is also known as the domain of the function, and B is called the range of the function. You can have multiple elements in set A and set B. So the input, which is the domain, is associated with the range, which is the output of a function. As I said earlier, the set of inputs is known as the domain of a function, and the set of output is known as the range of the function. And it can be like the binding can be associated with any rule. It can be as simple as multiplying the input by 2. It is also a function. Why? Because every input is bind to exactly a one output. For instance, if the input is 3, the output will always be 6. Not like it can't be other than 6. It is a exact mapping. That's why it is a function. Okay, so if it is not an exact mapping, in that case the f is not a function. Yeah, so vertical line test. So what exactly a vertical line test is? So according to the definition of this test, so given a function f, every vertical line that may be drawn should intersect the graph at exactly one place. Okay, so if this is the case, then you can say that the function f passes the vertical line test, and you can call it as a function. So for example, let's assume a sample function is given to you, a parabola is given, okay, and you need to ensure that whether it passes the vertical line test or not. So the test says if you pass a vertical line from the function, it should exactly intersect it at one place. Okay, so given the domain of the function, if you choose any x from the domain and draw a vertical line, so you will see that it always passes or always intersects the graph at one place. So therefore it passes the vertical line test. But at the same time, if this graph is given to you, okay, and you try to ensure that whether it passes the vertical line test or not, you draw a line. So you can see that it intersects the graph at 3 places. So therefore it fails the vertical line test and this passes. So this is what the vertical line test is. Okay, so if the vertical line intersects the set of points more than once, in that case it is not a function. It is not a function. Okay. So let's see an example, a very basic example. So given a function f, you need to evaluate what is the value of f square root of 2. Okay, so f of square root of 2, we just need to assign square root of 2 in place of x and evaluate. Okay, square plus 2 times x, which is square root of 2 plus 1. So which is 3 times 2, 6 plus 2 square root 2 plus 1. So it evaluates to 7 plus 2 square root 2. Okay. So given a function, you can easily evaluate if x is given to you, what is the value of y. And the function is generally a very popular nomenclature is y is equal to f of x. Okay. Here x is also known as the independent variable. And y is known as the dependent variable. Why? Because the value of y is determined by f of x. So y depends on x. That's why it is known as the dependent variable. And x is the independent one. Okay. Easy illustration. So now let's see what a domain and range of a function is. Okay. So every function has a domain. So it won't be a scenario in which a function is given to you. There might be a case the domain is not specified in the problem, but if there is a function, then it is always associated by a domain and a range. So every function has a domain, but sometimes the domain is not specified. You will see some scenarios in which the domain is not given to you, or a function is given to you, but you have been asked to calculate to find the domain and the range of the function. So if nothing is specified, then the assumption is the domain is a set of all real number x. So for all real number x, for which f of x is also a real number, which means if y is equal to f of x is given, so the domain of this function will be the all possible real numbers of x for which this f of x is also real. The value of y is also real. Okay. And real numbers you already know. The real number is anything which can be put on a number line is a real number. It can be positive numbers, it can be negative numbers, it can be 0, it can be rational numbers, it can be irrational numbers. So everything which can be put on a number line is a real number. So, or you can also say a non-imaginary number. So apart from imaginary numbers, which is of the form square root of minus something, say minus x or minus 5, it can be anything. Apart from these imaginary numbers, every other number is a real number. So yeah, again, if a domain is not specified, in that case you need to find all possible x for which f of x is also real. For instance, if f of x is x square is given to you and you need to find what is the domain and range of the function. So if you see the function is x square, f of x is x square. So in this case, you can have any possible value of x from the real number set. Okay, there won't be a x for which f of x is non-real if fx is x square. So the domain will be set of real numbers denoted by capital R, or you can also mention it like this. Yeah, and the range of this function fx is equal to x square will be all possible values of f of x. So in this case, it is a square function, it is a parabolic function. So therefore, all x, all positive real numbers, all real numbers which are positive. Why? Because fx is x square. So this will be the range and domain of this first function. So okay, so then we have one more. Fx is square root of x. So fx is square root of x. So in this case, you have to consider the scenario when the domain is not specified and you need to find the domain. So what the definition says, the domain is a set of all real numbers x for which fx is a real number. So all possible x for which fx is real will be the domain of this function. So if you place x as, say, if x is -1, in that case f of x is a non-real number. Okay, it will be iota. So therefore, all x which are negative in nature won't be the part of the domain of this function. Why? Because the range becomes non-real if x is less than 0. So therefore, domain will be all positive real numbers. Okay, that's it. So if domain and range are not specified, so you need to ensure that you need to find the value of x for which f of x is real. That's it. So okay, let's have another example. So given a function which is f of x is 3x plus 2 minus 1. You need to find the domain and the range of this function. Okay. So in order to find the domain, you need to see that all possible x's for which fx is real. So to ensure that this should be positive. This should be positive. Why? Because there is a square root in the definition of the function. So to be 3x plus 2 should be greater than 0. Therefore 3x should be greater than minus 2 and x should be greater than minus 2 by 3, greater than or equal as well. So this is the range, this is the domain of this function for all x. If x is greater than equal to minus 2 by 3, that will result into f of x to be a real number. This is the domain of this function for all x which is greater than equal to minus 2 by 3. Alright, since the domain is clear, let's see how we will evaluate or find the range of this function. So in order to find the range, the function says y is 3x plus 2 square root of minus 1. So you need to convert this expression in terms of x, which is x equal to some expression of y. So for that, I am moving minus 1 towards the left hand side. So it will be 3x plus 2 square root will be y plus 1. So if I square at both the places, it will be 3x plus 2 will be y plus 1 whole square. Therefore, x will be y plus 1 whole square minus 2 by 3 and this is 1 by 3. This will be the value of x in terms of y. Okay, and we have already evaluated the domain which is all x which is greater than equal to minus 2 by 3. So this expression is greater than or equal to minus 2 by 3. Okay, so we can put it here. This minus 2 by 3 will get cancelled. So it will turn out to be y plus 1 whole square is greater than equal to 0. Okay, which will be the case y plus 1 will be greater than equal to 0, which will give us y greater than or equal to minus 1. So this will be the range of this function. Okay, so the domain will be all x's such that x greater than equal to minus 2 by 3 will be the domain and range will be all y's such that y greater than equal to minus 1. Okay. Alright, we have one more example. So let's solve it. So in this, y is given as 3 divided by x minus 2. Okay, so we need to find the domain and range of this function. So in order to find the domain, so domain is all possible values of x for which this y is real. So to ensure this property, this should be real. To ensure this can't be 0, which is x minus 2. This should not equal to 0. So therefore domain will be all x such that x is not equal to 2. This will be the domain of this function. Okay, and when you rewrite this expression in terms of x, okay, it will be x minus 2 equal to 3 upon y. Therefore x is 2 plus 3 by y. So in order to find the range, the range will be, this can't be undefined. So to ensure this, y should not equal to 0. Therefore range will be all y's such that y is not 0. So this will be the domain and range of this function. Okay, so yeah, so there can be problems in such a way that rather than providing you the expression of the function, a graph is given to you, like in this case, and the domain and range is asked for this graph. So if you see it closely, there is a filled circle. There is a filled circle in this, at this point and at this point. So if you see something like that, this, in that case, this value and this value is included in the function. It is inclusive in nature. Similarly, this is also inclusive in the function. So therefore the domain will be minus 1, minus 2, minus 3, 1, 2, 3, 4, all possible values of x. So x can vary starting from minus 3. So you can have like starting from minus 3 till 4. So domain will be all x from minus 3 to 4, inclusive, all values from minus 3 to 4. And the range will be all possible y's, or the value of f of x, in such a way that x is varying from minus 3 to 4. So it will be 1, 2, minus 1, minus 2. So since minus 2 and 2 are inclusive in nature, so the range of this graph will be all y's from minus 2 to 2, inclusive. Okay, so if a graph is given to you, this is the way in which you can find the range and domain of the function. Similarly, at this point, you can see that this is inclusive, but this is not inclusive. So the point minus 1, minus 2, minus 3 and 1, the point minus 3, comma 1 is not part of the function. It is exclusive, not inclusive. Okay, so you need to ensure if a graph is given to you. So therefore here the domain will be all possible values of x starting from, so there will be two range. The first range will vary from minus 3 to 0. The second range will vary from 1 to 3. Okay, so the domain will be the union of two sets, which is minus 3 to 0, minus 3 not including but 0 is including, union 1 to 3, 1 inclusive and 3 exclusive. Why? Because 3 is not included and minus 3 comma 1 is also not included as part of the function. Okay, at the same time, similarly we can calculate the value of y's in which this function varies. So here the function varies from the value of y varies from from 1 to 2. So the range will be 1, which is exclusive, to 2, 2 is inclusive, union this minus 1. And you can see if you try to have the value, so at this point minus 1 is not included, but from this range, which is minus 1 to just before 3, minus 1 is included. So minus 1 will also be the part of the range, not from this point but from 1 to just before 3. So the range, the domain will be -3 to 0, -3 not including, 0 including, union 1 to 3, 1 including, 3 is not including. Range is 1 to 2, union -1. Okay. So just ensure that whether the point is inclusive or exclusive. Based on that, we can decide what is the range and domain of these functions. Yeah. So the next is increasing and decreasing functions. So what exactly increasing or a decreasing function is? So according to the definition, if a function f is increasing in nature, in that case, if for all x which are in the domain of this function or the interval I, such that f of x1 is less than equal to f of x2 when x1 is less than x2. Okay. So for instance, if in an interval, say I, this is the interval x1, x2. So in this interval, x2 is greater than x1. So therefore, f of x1 should always be less than or equal to f of x2 if x1 is less than x2. So if this property holds, this is a increasing function. And at the same time, if this less than equal to is converted to only less than, okay, for all x1 less than x2, in that case this will be a strictly increasing, it will be a strictly increasing function. Okay, the only difference between an increasing and a strictly increasing function is this equality. So increasing function will be less than or equal to. In strictly increasing, it will always be less than, not equality. Equality won't be there if the function is a strictly increasing function. And at the same time, a function f is decreasing on the interval I for all x, x1 and x2, such that fx1 is greater than equal to fx2 when x1 is less than x2. So this is the scenario in which a function is decreasing in nature, like this. This is x1, this is x2. So x2 is greater than x1, but fx2 is less than fx1. Okay. So here f of x1 is greater than equal to f of x2 when x2 is greater than x1. So if this holds, then the function is a decreasing function. And at the same time, if I remove this equality and only say f of x1 is greater than f of x2 when x1 is less than x2, in that case this will become a strictly decreasing function. The only difference is this equality. Okay, so let's see an example. So in this case, the a part, the function is y is x and the b part y is minus x cube. Let's assume x1 is 1 and x2 is 2. Okay. So for the a part, we need to tell whether the function is increasing or decreasing. So for the a part, fx1 will be x, which is 1, fx2, x2 is 2. So fx2 will be 2. Okay. So in this case, x1 is less than x2 and at the same time f of x1 is also less than f of x2. So therefore, this is a increasing function. Okay. For the b part, y is minus x cube. So let's calculate f of x1. So f of x1 will be minus 1 times 1 cube, which is minus 1 only, and f of x2 will be minus times 2 cube, which is 8. So here x1 is less than x2, but f of x2 is less than f of x1. Therefore, the nature of the function is decreasing. That's why it's a decreasing function. Also, if you like plot the graph of these functions, so you can also plot them. So the A part, the graph will look like this. This is y is equal to x. Okay, so it is increasing in nature. If you cut out any interval, you will see the nature of the graph is, the nature of the function is increasing. And at the same time, if you plot the second one, the B part, so the graph will look like something like this. Okay, this is the graph for y is equal to minus x cube. So if you cut any interval here, so this is x1 and this is x2. So nature is always decreasing. Okay, so the B part is decreasing and the A part is increasing. All right, let's discuss the composite function, like combining multiple function in order to have composite functions. Okay, so let's assume two functions are given to you. Here f of x is x square and g of x is 3x plus 1. So you can form a composite function which says that you can define f of g x. Okay, given two function, fx is x square and gx is 3x plus 2. You can define f of gx, which is the composite function. Also, like it is read as f of gx, which is f of g of x. Okay, so in order to evaluate it, you need to replace gx in f of x here. Okay, so it will be three x plus 1 whole square. Why? Because f of x is x square. So it will evaluate to 9x square plus 1 plus 6x. So this will be the value of f of g x. And same time you can also have g of f of x. It is also similarly you can also evaluate this, which is g of fx. You need to replace f of x in this expression in order to get what is the value of g of f. So it will be 3x square plus 1. So g of f will be 3x square plus 1. So this is what a composite function look like. Okay, you can evaluate f of g of x, you can evaluate g of f of x. Alright. And now the point comes, why do we study these composite functions or combination of functions? So the only point is basically the real life problems or real life situations are not that easy, in which you need to have a result in order to analyze a single function or a single parameter. So in order to deal with complex problems, we do study composite functions or combining multiple functions based on various mathematical operators. So like one example, a very basic example, we can think of calculating the profit of a specific product. Okay, so if you sell a specific product, so the profit will be the revenue that came from that product minus the expenses, which is the cost. So a very basic function will be, let's assume P is the profit function of the article X, which is R of X, which is R is the revenue minus the cost of X. So this is a very basic example. In order to find a profit of article X, it is revenue minus the cost. Okay, so similarly, based on the problem, based on the issue which we are trying to resolve, we need to study these composite functions. Okay. Alright, so now combining functions, with mathematical operators. So in the previous slide we saw what a composite function is, which is f of g or g of f of x. But the functions can also be combined using mathematical operators or like mathematical operations. The first is sum operation, denoted by given two functions f and g. The notation will be f plus g of x, and the expression will be f of x plus g of x, which is add the outputs of f and g. The output of f is f of x and the output of g is g of x. So add them to get f plus g of x. Similarly, the second one, difference f minus g of x, which is subtract the output of g from f of x, fx minus g of x. The product will be f dot gx, which is f of x into g of x. You multiply the outputs of both f and g. And finally, dividing, which is f divided by g x, which is f of x divided by g of x. One thing to notice is you need to ensure that gx should not be 0. Otherwise, this f by gx will be undefined or non-real in nature. Okay, so divide the output of f by the output of g. And like one more thing you have to notice is we see this product which is denoted by f dot gx. This is not equal to the composite function that we studied in the previous slide. The composite function f of g of x. These are two different things. The first one is the product operation between f and g. The second is the composite function of f of g. It is why they are not equal, which is because the left hand side is f of x times g of x, and the right hand side, which is not equivalent to the left hand side, is f of g of x. That's why this is denoted by a single dot and this is denoted by a small o or circle. So you need to see it very carefully that these are not equivalent. Okay. So let's have an example. Given two functions, fx is 2x minus 3 and gx is x square minus 1. You need to find these following combination of function based on the mathematical operators that we saw in the previous slide. So the first is addition, the sum f plus g of x. So f plus g of x. So it will look like f of x plus g of x, which is 2x minus 3 plus x square minus 1. So it will evaluate to x square plus 2x minus 4. Okay, so this is the A part. Similarly, we can calculate for B, which is f minus g of x. F minus g of x will look like 2x minus 3 minus x square minus 1, which is minus x square plus 2x minus 2. Okay. Similarly, we can solve for the third one, which is f dot g x, the product of both of them. Two x minus 3 times x square minus 1. Okay. So the product will be 2x cube minus 2x minus 3x square plus 3. And finally, f divided by g x, which is 2x minus 3 divided by x square minus 1. Okay. So yeah, that's it for the combining function based on the mathematical operator. One part you can take it as a homework. You need to find the domain and range of all possible of all these four options. Okay, and do ensure what will be the range and domain of this f by g of x. Okay, calculate it carefully. So let's see one more important definition for the composite function. So it says consider function with domain A. Okay, so f is given and the domain of f is A and range B. So f is defined as a function from A to B. Okay, this is f. And the same time the function g is defined with domain D and range E. So you have another function with domain as D and range as E. This is G. So the definition says if B is a subset of D. So if B is a subset of D, so I can say that there is another set which is D, a superset of B. It is another way of saying it, B is a subset of D. Then the composite function GOF of x is the function with domain A. Okay, so what is the definition? If B is a subset of D and D is the domain of G, in that case the domain of G of fx will always be A. So this is what we're trying to say. Okay, so A will become the domain of G of fx. G of f of x. A will become the domain of G of fx when B is the subset of D or D is a superset of B. So one question here. So can we say this thing, if B is the subset of D, can we comment upon the range of GOF? Can we say that range of G of fx is equal to E if B is subset of D? Just pause for a minute and think over it. Can we say this or not? Okay, so let's have an example to understand the definition that we saw in the previous slide. So in this example, I have two functions f and g. A and b are the domain and range of f, and d and e are the domain and range of g respectively. Okay, so let's see whether we can comment about the range of GOF and compare it with the range of E. So if I have to create a map of f and g at the same time with GOF, so you have to take this A, which is 1, 2, 3. So let's see the mapping of f, g and GOF. Okay, so this is A. Then we have range of f, which is B, 0, 1 and D. So like this example, I have ensured that B should always be the range, the subset of D. So 0 and 1 are the subset of D. So here B is subset of D. So making a 2, 3. So this is D, and in this D we have this B. Okay, and now finally E, which is 3, 4 and 5, 3 elements in E. So I have to create a map of f from A to B. So one is mapped with 0, one is mapped with 0, 2 is mapped with 1 and 3 is again mapped with 0. So this will be the mapping of f. This is f. Again I can map D to E. This is E. I can map D to E. 0 is mapped with 4, 1 is mapped with 5, 2 is mapped with 3 and 3 is mapped with 5. this will be the mapping of G looks like. Okay. So if I have to calculate, if I have to find the mapping of G, O, F, this is what we are trying to find, right? So this is G of Fx. So let's have this mapping starting from A, which is F. So we have A, the possible value of, we have X, then we have G of Fx. Okay. So if X is 1, what will be the value of G of X? If X is 1, what will be the value of G of F? So this is mapped with 0 and 0 is mapped with 4. So it turns out to be the value of G of F will be 4 if X is 1. Okay. So now what if X is 2? So 2 is mapped with 1. So F of X will be 1 if X is 2. F of 2, which is F of X, will be 1. And G of Fx will be G of 1 and G of 1 will be 5. So if X is 2, G of F comes out to be 5. And similarly we can evaluate for 3. If X is 3, then it is mapped with 0 and 0 is mapped with 4. So it turns out to be if X is 3, it will be 4. Okay. So seeing this mapping of X and G of Fx, we can easily say that the domain, this all the values of X, this is equal to the domain of F. This is the domain of F. This is, and it is also the domain of F, and it is equal to domain of G of F. Domain of F is equal to the domain of G of F. Why? Because B is subset of D, we have seen in this example. But at the same time, if you see the range of G of F, the range of G of F is not equal to the range of G, which is E. Why? Because there is an extra element 3 which is present in E but not present in G of F. So therefore, if this holds true, which is B is subset of D, the range of G is not equal to the range of G of F. And in fact, the range of G will always be the subset of G of F. You can see this 4 and 5. This contains two elements, 4 and 5. And range of G has 3 elements, 3, 4, 5. So this will always be the subset of range of G. And when it will become equivalent, it will always be equivalent if B is equal to D. If B is equal to D, in that case the range of G will be equal to the range of G of F, or else it will always be the subset if B is subset of D. Okay. So let's see an example to find the domain and range of these composite functions. So in this example, fx is defined as x square plus 1 and gx is defined as 1 by x. We need to find what is the value of g of f and f of g and their corresponding domain and ranges. So let's see how to do these sort of problems. So first of all, we need to find the values of g of f. We need to evaluate what is the value of g of f. So it will be g of fx. So what I will do is to find it, I will see what the value of gx is and then just place the value of fx over there, in g of x. So it is 1 divided by x. So I will just replace the value of x with f of x. So it will be 1 upon fx, okay, and fx is x square plus 1, which is 1 by x square plus 1. This is the value of g of f. Similarly, we can calculate the value of f of g. which is f of gx. So what is the value of f of x? It's x square plus 1. So it will be 1 by x, which is g of x square plus 1. So it's 1 by x square plus 1. Okay. So these will be the corresponding value of f of g and g of f. So now the next task is to find the domain and range of these functions. So in the first part, g of f is x square plus 1. So I can write it as equal to y. Okay. So I'm just simplifying. I'm replacing g of f with y. So y is equal to 1 by x square plus 1. So we need to treat it as a independent function and then find the domain and range accordingly. Similarly, this is also, I can say this is also equal to y and treat it as an individual function and then evaluate the domain and range. Okay. Once we get these functions. So if I see this, y is equal to 1 by x square plus 1. So the domain will be all possible values of x for which the function is returning a real number. So in this case, x square is always positive and plus 1. So there won't be a case in which this turns out to be 0 or not defined. So the domain will be all real numbers. Set of all real numbers will be the domain. And similarly, in this case, which is y is 1 plus 1 by x square. Here we need to see it carefully. There is one value of x which is 0. If x is 0, in that case y becomes undefined or non-real. So for this function, the domain will be all x's, x belongs to real number such that x not equal to 0. Except x is equal to 0, everything is present in the domain of this, which is f of g of x. So now when it comes to range, let's see for the first one. To find the range, we need to convert it into an expression such that x is equal to y. So it will be x square plus 1 is 1 by y, and therefore x will be 1 by y minus 1 square root plus minus square root of 1 by y minus 1. Okay. Now we need to find all possible values of y such that x is also defined, which is a real number present in the domain, which is R. So in order to ensure that x is in the domain, 1 by y minus 1 should always be greater than 0. Okay, which is why, because it is under the square root. So it should always be greater than 0. So if you see it, if you evaluate it, 1 by y minus 1 should be greater than equal to 0. So 1 by y should be greater than equal to 1. Then y should be less than equal to 1. So it's 0, it's 1. So all values less than 1 will be the part of range. Okay. But the answer is no. We need to also ensure that this should always be greater than 0. So if you place anything, if you choose y in such a way that it is less than 0, then x will always be a imaginary number, a non-real number. For example, let's assume minus 1. Just put y as minus 1. So x for y minus 1, x turns out to be plus minus 2 iota. So it is an imaginary number. So everything less than 1 but should be greater than 0, and 0 is not including y. If you place y as 0, it will be 1 by 0, which is undefined. So everything this will also be the part. So the common range turns out to be 0 to 1 excluding 0. 0 to 1 excluding 0. So for this, the range, let me write it here, the range will be 0 to 1, 1 inclusive, 0 exclusive. Okay. Similarly, for the second part, f of g, so we already have the function. We can simplify it in terms of x. So it will be simplified as 1 by x square is y minus 1. Therefore, x square will be 1 by y minus 1 and x will be plus minus square root of 1 by y minus 1. Okay, so for this to hold true, this should always y can't be 1. If y is 1 and if y is 1, then this becomes undefined, 1 by 0. So therefore range will be everything except 1, and at the same time this should always be greater than 0. So y minus 1 should always be greater than equal to 0. Not 0, it should be always be greater than 0. So y should be greater than 1. Therefore the range is all possible real numbers such that y is greater than 1. It will be the range of f of g. Okay. Alright, then comes symmetry of function. What exactly the symmetry is and why it is important. So the symmetry in functions refers to how a graph behaves when reflected across an axis. So if you see a reflection of a graph, if you see a reflection of a function, so how it is behaving tells about the symmetry of that specific function. Okay, and generally there are two main types of symmetry which is commonly being used. The first is even functions. So it is a specific set of functions which are symmetric about the y-axis. And what do I mean about symmetry about y-axis? So if you plot the graph, this is x-axis, this is y-axis. So symmetry about y-axis is if you place a mirror over here, over the y-axis, the left hand side will be the mirror image of the right hand side. Okay, it will be the mirror images. So for example, let's you can have a parabola. Let's assume this. Yeah, so the value of this is, say, x is c and this is x minus c. So what symmetry means? For both the values, if x is c and x is minus c, for both of them the value of y is same, which is f of c and f of minus c. They both are equivalent. Okay, so this is the definition of even functions. So when can we say a function is even? If f of x for any x is equal to f of minus x for all x belongs to the domain. Okay, so if this equation holds, then the function turns out to be a even function. Okay, then comes the odd function. So this is another form of symmetry in which the symmetry of a specific function is about origin and not the axis. So there is also an equation for that. The condition is f of x is equal to minus f of minus x. If this equation holds, for all x belongs to domain of fx. If this equation holds, in that case you can say that the function is an odd function. A very basic example, y is equal to x. So this is symmetric about the origin. You choose any x, say x is 3 and x is minus 3. So f of 3 turns out to be 3 and f of minus 3 will be minus 3. So according to the definition, f of 3 should be equal to minus of f of minus 3, which is 3 is equal to minus of minus 3, which is equal. So 3 equal 3. So if this equation holds for all x in the domain, then the function is an odd function. Okay. So let's see an example. So here are 4 options. You need to tell which is an odd function or which is an even function. So we can easily calculate. How? If fx is equal to f of minus x, it's even. if fx is equal to minus of f minus x, it's odd. So we need to check which of these holds these two equations and then comment accordingly. Okay. So for the first part, fx is present. We evaluate f of minus x. So f of minus x will be minus x to the power 4 minus 2 minus x square minus 3, which is x4 minus 2x square minus 3, and it is equal to f of x. Therefore it's even. Okay. Similarly, for this one, evaluate what is the value of f of minus x. It will be minus x cube minus 4 times minus x, which is minus of x cube minus 4x, and it is equal to minus time f of x. Okay, so therefore it's a odd function. Similarly, you can calculate for cos and sine. It will be even and it will be odd. And finally, if fx is e to the power x, it will be f of minus x will be e to the power minus x, which is 1 divided by e to the power x. So it is neither equal to f of minus x nor it is equal to minus of f minus x. It is neither equal to f of x, it is not equal to minus of fx. So in these sort of scenarios, so the e part, which is fx is e to the power x, there are possibilities that the function is neither even nor odd. So this is an example where it is neither even nor odd. It is very much possible. Okay. Alright, so that's all I have for this lecture. I hope you guys enjoyed this. See you in the next class.